I'm going to record this and I will post this online in case anybody wants more. I'm also always happy to chat. And especially if there are any graduate students here, I have a lot of opportunities for mentoring undergraduates. So if you're interested in stuff like this, I'll be here giving a talk to the undergraduates at either 4 or 5 o'clock, something like 4:30. 4:30. There we go. Split the difference. And if you're interested, you would love to talk to you about stuff like this. So what I want to talk about is the theory of the distribution of zeros of L functions, what we have to try to understand them, what kind of problems we look at, what kind of techniques we use. I will have far more slides here than I will go through, so that if you really want to see some of the technical details, the slides are at least easily accessible to you, but it's much better to just email me and I'll give you some really nice surveys written by a variety of people that explain how we came to these. So the first is, I'm not sure who's in the audience, so I will start off by admitting that I am married to a marketing professor who has taught me you have to motivate your subject. Why do we care about zeros of L functions? Why do we care about the zeros of the Riemann Zeta function and other things? So here's a couple of problems you can look at. I could be interested in trying to prove that there are infinitely many primes or primes in arithmetic progression. Or I could be interested in more finer questions about how many primes do I have congruent to, say, 3 mod 4 versus 1 mod 4. And it turns out most of the time, and this can be quantified, there seem to be more primes 3 mod 4 than 1 mod 4. Or we've got people who do elliptic curves here. You might be interested in the Birch-Swinnerton-Dyack conjecture, the order of the group of rational points on elliptic curves. You might be interested in things such as the class number. And it turns out a lot of these questions are related to zeros of the Riemann Zeta function and its generalization L functions. And the quick 10-second seminar philosophy is, the more you know about zeros, the more you should be able to say about a bunch of problems of interest. So if you want to prove just the main term in the prime number theorem, that there's x over log x primes up to x, you just need to know that the zeta function doesn't vanish on the line real part of s equals 1. And similarly for primes in arithmetic progression. If you want to get a better result about what are the error terms, then you need the Riemann hypothesis or the generalized. It's believed that all the zeros that are non-trivial, the negative even integers, they should all have real part 1/2. The closer you get to proving that, the better results you get on the error terms and counting how many primes there are. Then things like Chebyshev's bias, that there seem to be most of the time more primes that are 3 mod 4 than 1 mod 4. The Riemann hypothesis is no longer enough. What you have to do now is you have to say, well, let's look at the zeros on the line real part of s equals 1, and let's assume that there's no relation between the zeros involving rational multiples. It would be really strange if some kind of rational linear combination of them vanished. So this is the grand simplicity hypothesis. And then going even further is you can talk about spacings between zeros. So if you count primes, you know that as you go further and further up, the average spacing between primes is increasing, so that if you're at height x, you expect to have about log x to go before you find the next prime. If you look at zeros, it goes the other way. The further up you go, the denser the zeros become. So you can unfold and you can readjust so that you now have a sequence that has mean spacing 1. And you can ask questions such as, well, how often do I have 2 zeros that are less than, say, half the average spacing? Or how often do I have zeros that are twice the average spacing? And results along those lines turn out to have things that they can say about the class number. So most of the research I do in my life can be classified to, I have some system, I observe some values T1, T2, T3, and I want to understand what rules govern how long I need to wait. If you need to motivate this to your students as to why you might care about this, one of the examples I give is that when I was young, when you went to a bank, there might be 4 tellers and each teller had a line. Now there's often just one line and you go to the next available teller. The average wait time doesn't change, but what changes is the variance in how long certain people wait. So if you have one person who has an extremely detailed transaction that's being done that requires a tremendous amount of work, they don't kill the time for everybody behind them. That's pain is kind of spread out a little bit among everybody. So there's lots of different systems you can study. I started by working with a nuclear physicist who was sick and tired of, if you were lucky, you had maybe 1,000 data points in nuclear physics after months of hard work, whereas if you're looking at zeros of L functions, you can calculate billions of zeros in almost no time. So he became interested in number theory. I should have said this earlier, I'm from Boston. If you have any trouble understanding either the Boston accent that I can help you with. And I will also try to help you with the physics accent, because I was trained as a physicist and I moved into the subject. So at times I speak as a physicist would. And I have tried to always, when I give these talks, to change and convert to using the math language. But later in the talk, I will actually give you how a physicist would look at a lot of this. Well, instead of studying the energy levels between heavy nuclei, you could study eigenvalues of matrices. So if I choose matrices at random, and there are different ways, some of us at lunch were talking about on general exams being asked to prove the construction of Haar measures. You could construct your space of matrices using Haar measure. You could choose your entries of your matrix maybe randomly from fixed probability distributions. And you can ask, what can you say about the distribution of eigenvalues? And it turns out a lot of these problems are all related, that you'll see similar behavior in many different things. So it turns out in many different settings, we have to do three things. We have to first determine the correct scale to study events. So we talked about primes. If you go high up on the line, the average spacing between primes is about size log x. This is why twin primes are so difficult, because the average spacing is of size log x. 2 divided by log x is extremely small. So we have to figure out what's the right scale to study things. If I look at an n by n matrix, what do I expect the size of the eigenvalues to be as a function of the matrix size? And then if I figure out what the correct scale is, I might have something that will have some nice limit as I let something tend to infinity. The next is to develop an explicit formula relating what we want to study to what we're able to study. So one of my favorite results in linear algebra is the eigenvalue trace formula, which gives you the trace of the matrix, the sum of the diagonal entries, is equal to the sum of the eigenvalues. So if you choose the matrix elements at random, you have knowledge about the matrix elements, but you want to figure out things about the eigenvalues, because that's what tells you what's going on for the system. The eigenvalue trace lemma allows you to pass from one to the other. So we need some kind of analog for two. This is where the number theory comes into play. We sadly do not have as good results for L functions in number theory as we do in random matrix theory. So the results will not be as good. And then the last is we need some kind of averaging formula. It's great that the eigenvalue trace lemma allows us to pass from the eigenvalues to the matrix elements. But now we need to be able to do something with those functions of the matrix elements. And if we can't, then this is just converting from one hard problem to another. So we need some kind of averaging formula. Okay, so just to make sure we're all on the same page, if you've never seen it before, this is going to be a really fast introduction. This is the Riemann zeta function. It is defined as the sum of 1 over n to the s, where n ranges over the integers. And by using the fundamental theorem of arithmetic, every integer has a unique factorization of primes in increasing order. You can write it as a product over primes. It satisfies a functional equation. Its value, the completed zeta function, its value at 1 minus s equals its value at s. It also satisfies the Riemann hypothesis. I know because I've checked the archive and there's numerous proofs there that it satisfies. In fact, you were kind enough to show me another one today. All the non-trivial zeros have real part 1/2. And there's a really nice interpretation. If this were true, there are some talks about trying to interpret the zeros of the Riemann zeta function, maybe like the eigenvalues of some kind of physical system, the energy levels of some kind of physical system. And it turns out that the spacings between zeros look very similar to the spacings between the eigenvalues of complex Hermitian matrices. So unfortunately, I guess when I project on Zoom like this, you miss out the very bottom line. You can see that there's probably something there because there's almost surely not going to be just a perpendicular symbol looking like that. So it just says that the spacings between zeros appear the same as the spacing values between eigenvalues of complex Hermitian matrices. So this was a numerical observation. And for a while, people thought that maybe this meant that there's some kind of physical system going on. A lot of times in quantum physics, you have some kind of operator you can write down as a matrix. The energy levels are related to the eigenvalues. And maybe there's something like this that we can do for the Riemann zeta function. Well, rather, yes. So the story is that when Montgomery was a graduate student, he was visiting the institute. And he was, so you should talk to the great mathematical physicist Dyson. He always loves to know what people are doing. And Dyson says, so what are you up to? Well, I'm looking at the pair correlation statistics, which we'll get to later. And I noticed the following. And Dyson goes, that's amazing. That's exactly what we see when we look at random matrices and nuclear physics. And this wonderful conversation then has led to 5 decades of conversations between physicists and mathematicians, where you see very similar behavior in extremely different systems. And the methods of proof are very different in random matrix theory versus number theory, but you get the same type of results, the same type of behavior at the end, which is absolutely amazing. Well, instead of studying just the Riemann zeta function, 1 over n to the s, I can basically have almost an identical slide where I replace 1 with just some coefficients af. And I want my coefficients to be such that I have a product representation as well. Yeah, so right. So it just says it's the same as the eigenvalues of complex emission matrices.
Oh, it's not like a control minus.
Yeah. So it's, if I go like this, no, that's.
Hide something.
Yeah, I'm trying to say hide self view. Let's try that.
No, that's what you were in.
That's what I was in before. Yeah. And then is that readable? All right.
That's good.
So if that's readable, let's do it like that. Yep. Okay.
It's a smaller problem.
The other thing is I can just go like this. I'll do my best Vanna White. And so I can replace the 1 in the Riemann zeta function with AF, and I want to have an Euler product. So it's extremely important that I can write this as a product over primes, and we'll see shortly why this is so essential in everything we're going to do. And we have a completed L function. There's some factors you put in here that relate its values at 1 to its values at 1 minus s. Depending on what type of math you do, you might have slightly different formulas here. If you're doing elliptic curves, you might do s goes into 2 minus s. So hopefully everybody is friendly and doesn't mind if we just normalize like this so that all L functions have the same functional equation. It's believed if you have a nice L function, the generalized Riemann hypothesis will hold and all the non-trivial zeros will have real part of s equals 1/2. And again, it was observed that the properties between the eigenvalues of complex emission matrices seem to be behaving similarly as the zeros of these L functions. And so, one of the first bits of information or evidence we have towards this was looking at the gaps between 70 million consecutive zeros of zeta starting at the 10 to the 20th zero. So this is due to Andrew Odlisker, an incredible calculation starting at the 10 to the 20th zero. And just looking at 70 million consecutive ones starting from that point, the solid line is the prediction from random matrix theory. And you see just an incredible fit in terms of what's going on between the spacings between adjacent zeros. All right, so I promised that this talk would be accessible and I would try to explain big picture, why do we want an Euler product, for example? Well, I tell my students that whenever you see a product, you should have a Pavlovian response, you should take a logarithm. We know how to deal with sums, we don't really know how to deal with products as well. Well, the log of a product is the sum of the logs. So if I take the logarithmic derivative of zeta, well, the log of a product is going to be the sum of the logs, and then I can differentiate term by term. And when I differentiate term by term, I'm going to get the following formula. I can then expand out the denominator using the geometric series formula. And as long as s is sufficiently large, 1 over p to the s will have absolute value less than 1, and I can expand things out. And when I expand things out, I keep the main term and everything else we'll call good. It turns out you can just work with all of this and you can do standard complex analysis stuff. So if you've taken complex analysis, one of the things you learn is whenever you have a function, you do a contour integral, you shift the contour, you pick up contributions at the zeros and the poles. And so if we do a contour integral of zeta prime over zeta times x to the s over s, if we shift the contour, we're going to get a contribution from the pole of the zeta function, and it's going to give us an x. And then all the zeros, if they have real part 1/2, they'll be giving us terms like x to the 1/2. That's going to be a smaller contribution. And this is roughly how you can see the Riemann hypothesis coming in. Why is this related to primes? Well, if I do a contour integral of this side, I've got to integrate this side as well. So I have the integral, I pull the sum of p outside of that, and I'm integrating x over p to the s. Well, if p is less than x, this integral turns out to be 1. If p is greater than x, it turns out to be 0. So this is just going to detect the primes that are less than x, and it's going to weight them by a log p factor. So log p doesn't really change that much. You can then play games and you can remove these log weights, And you can get formulas for counting primes related to information about zeros of the zeta function. Well, this is if we integrate zeta prime over zeta against x to the s over s. Well, there's other functions we could do. And rather than x to the s over s, I could just do some nice test function phi. And so if I do some test function phi, if I look on the right, I have phi to the s times p to the negative s. Well, if I rewrite p to the negative s as e to the negative s log p, and I write s as sigma plus it, you can see this is looking like a Fourier transform. And so what I can do is, this is my explicit formula. I'm going to relate something involving zeros of the zeta function. So phi will be evaluated at zeros of the zeta function. And on this side, I'll have phi hat at things related to the primes. And so knowledge of the zeros gives information on the coefficients. So this is the analog of the eigenvalue trace lemma. So for example, if I look at a family of cuspidal new forms, if you haven't seen what they are, doesn't really matter too much. I can get what's called an explicit formula. And I'll have a sum of my test function at the zeros of my form. And on the right-hand side, I'll have things involving sums over primes and the coefficients of the stuff. It's very hard to look at one function. And so rather than just looking at one function, it's much easier if you look at a family, if you look at a lot of L functions that have properties in common. And I'll talk more about that shortly. So there's a bunch of statistics that one can look at. So the first statistic that was looked at was the n-level correlation. And for the n-level correlation, you look at a bunch of zeros and you look at how often, let's just do the pair correlation. So how often is one zero minus the other? How often is that in a box? So I look at all indices I and j, and I see how often is, say, alpha j1 minus alpha j2 in an interval I. Well, one L function has infinitely many zeros. And as you go higher and higher up, the zeros become closer and closer and closer. You can rescale the zeros if you want. They have maybe mean spacing 1, but as you go higher and higher up, you'd have to constantly be adjusting the scale. Since there are infinitely many zeros, I'm looking at what fraction of the time of, how many pairs do I have divided by, say I'm looking at all indices up to n, how often is that in an interval? Well, if I throw away finitely many zeros, since the zeros are going to infinity, in the limit, it's not going to change the behavior. So statistics like this are insensitive to the behavior of finitely many zeros. In particular, if you've studied elliptic curves, what's going on at the central point, this is the Birch-Swinnerton-Dyer conjecture that the order of the Mordell-Weil group, of the number of rational solutions is equal to the order of vanishing of the L function at the central point. Well, this completely misses that. It can't understand anything like it. But one L function has enough zeros to study a statistic like this because the number of zeros is getting larger and larger and larger in each interval of width 1 as you go higher and higher up. So you don't need to average over similar L functions if you're just looking at n-level correlations. So there were a lot of results. There was the numerical result of Odlyzko, which we talked about, that the zeros, the spacings between zeros of L functions look like the spacings between eigenvalues of complex emission matrices. Montgomery proved that the two-level correlation of the Riemann zeta function, so this is alpha I minus beta j, alpha I minus alpha j, how often is that in an interval, that seemed to agree with random matrix theory. Dennis Hedgehog then proved the same thing for the 3-level. And then around the same time, Rudnick and Sanak proved not only do the n-level correlations of zeta agree with the random matrix theory, but actually not just for zeta, but for all automorphic cuspidal L functions. So you're seeing an incredible universality here, that all of these L functions are behaving the same as you go far away from the central point. So you can't really tell the difference between the behavior of Dirichlet L functions or elliptic curve L functions as you go farther and farther up the critical line. And then things got really interesting when Katz and Sanak showed that the n-level correlations of all the classical compact groups are also the same. And so we're seeing this great universality, but maybe we're seeing the universality because we're not looking at the place where things are interesting. Things are interesting near the central point. This is Birch-Swinnerton-Dyer. This is where things are happening. And so we need a new statistic that's going to focus on what's going on at the central point. The n-level correlations is insensitive to finitely many zeros. We want something that depends mostly on what's going on near the central point. And so this led to a new statistic called the n-level density. And the way the n-level density works is you take a Schwartz test function, so function it's differentiable, it and all of its derivatives decay as fast as you want, so that you never, ever, ever have to go back to your analysis prelims and say, okay, what do I need to make sure that these things converge? Everything converges, you don't have to worry about anything. I'm going to assume I can write my function as a product in each variable so that it factors nicely. You don't have to do this, it just makes the calculations a little bit easier. And so what I'm going to do is I take one of my functions, if you want to think Riemann Zeta function, and I'm going to sum over distinct zeros, and I'm going to take each test function and weight it by one of the zeros. I mean, that's where I'm going to evaluate things. And because phi is a Schwartz function of rapid decay, the further I go away from the origin, the smaller things are going to be. And there's a couple of things to notice here. The first is I'm rescaling the zeros by some parameter. This is designed so that the mean spacing is 1 near the central point. The second thing is I'm summing over distinct zeros. It's not a big deal to sum over distinct zeros. If I do the 1 level density, well, there's only 1 0, so distinctness doesn't even enter at all. If I do the 2 level or the higher, it's just a combinatorial inclusion-exclusion game. If they have to be distinct, okay, well then let me add back when J1 equals J2. It just turns out that this object is a little bit more tractable to work with and has some nice analogs on the random matrix theory side, but through combinatorics, it's really not a big deal to do one or the other. What's nice about this statistic is now individual zeros contribute in a limit. And in fact, which zeros contribute the most? It's the ones near the central point. And the idea is we can do this for one L function. So if we take a bunch of L functions, for each one of them, we can look at what's going on, and then we average over them and we get some kind of average behavior. So I was fortunate to be in this area about 2 weeks ago for Mason 6. And Larry was talking about the 3 things you can do in number theory. And I was arguing that there's a 4th thing you can do. Oh, sorry, an analysis. Yes. Sorry, analysis. There's 3 things you can do in analysis. The 4th thing that I would like to suggest is that if your problem is too hard to study, embed it in a family and prove a result on average. And then, you would love to say a generic object is close to the system average, which you can sometimes do. So it's very hard to say what's going on for a specific L function near the central point. But if I put things in a family, I can say, on average, I know what's going on near the central point. Okay, and so the Katz-Sarnak density conjecture is that if you have a nice family of L functions, if I take the statistic for each L function and I average over a family, that should converge to something that depends only on a symmetry group attached to the family of L functions. And different families of L functions will now have different behavior for what's going on average near the central point. And so the calculations can become a little bit tricky. A lot of it depends on the difficulties of renormalizing the zeros. And I don't think you want me to go into the technical details. If I'm wrong, I'm happy to chat with you afterwards. There are games you can play in terms of how do you rescale the zeros. One of the challenges is when you average over the family, you want to be able to push the average over the family through the test functions and hit the coefficients when you use the explicit formula. If each form has to have a different normalization, that's going to make things harder. And unfortunately, once you start looking at the 2-level density, there's no way to get around this. You have to handle technical issues like this. And the hope is that if you take what's going on for each F in your family and divide by the number of elements in your family, and then let the family go to infinity. So if you've seen Dirichlet L functions, think Dirichlet forms, Dirichlet characters of conductor n. Maybe n is prime, and then you let n go to infinity through the primes, and you try to see what happens with that. Or cuspidal new forms of level n, let n go to infinity. And the hope is that this will then converge to something nice, integrating phi against some function w. Well, what are the answers that you get? Well, it turns out the classical compact groups, unitary, symplectic, orthogonal, and orthogonal can be split to SO even, SO odd. So the biggest difference is SO odd has a forced eigenvalue at 1. They have different 1-level densities. So this breaks the universality we saw with the n-level correlations, which is terrific. Unfortunately, if you look at what's going on, you have the delta spike, and then you have this function eta of u, which is 1 if u is less than 1, a half if u equals 1, an absolute value, and 0 otherwise. Well, the 3 orthogonal flavors, it turns out they all have the same Fourier transforms of this function we're integrating against, if your support is between -1 and 1. So we want to take a test function phi such that phi hat is supported is 0 outside of minus sigma sigma. I can't tell the difference between the 3 orthogonal flavors. This means I could have a family of L functions that have odd functional equations, but I can't distinguish their behavior from an even family if I only look at the 1-level density. In my thesis, I said, well, just look at the 2-level density and then you can see a difference immediately, but then you have to understand the sign of the functional equation. Well, it's not surprising that the sign of the functional equation should play some kind of role here. And so I promised I would translate, translating from Bostonian is hard, physics to math is not so bad. And so here is the dictionary. So in mathematics, we study zeros of our function. In physics, they'll study energy levels. One of the best quotes I ever heard is the way you understand the structure of subatomic particles is you take 2 subatomic particles, accelerate them towards the speed of light, crash them together and see what comes out. So imagine trying to understand how a grandfather clock works by taking 2 grandfather clocks, accelerating them to the speed of light, looking at all the gears and cogs that fly out and trying to deduce the internal structure. Well, this is what physics does. They shoot neutrons into the energy, into the nucleus. And by what comes out, they try to understand the internal structure of the nucleus. Well, instead of shooting a neutron, we shoot a Schwartz test function. Now in physics, they can't shoot a neutron of arbitrary energy. They can only shoot neutrons whose energy lives in a certain window. And it's the same thing in number theory. For us, it's the support of our test function. We would love to shoot in an arbitrary test function. If I could take my test function phi to be the delta spike, it would give me only what's going on at the central point. Well, that's where Birch-Swinnerton dia is. Great. I would have the answer. Unfortunately, the Fourier transform of the delta spike is the function that's identically 1, which means you would have to understand the prime sums over everything. And we just can't handle sums like that. We can only handle sums over primes in certain restricted ranges. And so there really is a nice analog between the number theory and the physics. There's a lot of different results about all these different families where you can see agreement between number theory and random matrix theory predictions. I'm not going to go into details, but there's a huge body of work where a lot of people have studied a lot of families and just shown that, yes, we see the same behavior in very different systems. All right, so again, there's 3 steps. The first is you have to somehow control the conductors to figure out what the scaling is. The second, and we talked about this with the product formula and taking the logarithmic derivative and doing the contour integral, is we need some kind of explicit formula relating sums over zeros to sums over primes. And then the last is we need some type of averaging formulas. And for those of you who want to do automorphic form theory, the more averaging formulas you get, there are plenty of results in the subject that are waiting for stuff like that, where once we have better averaging formulas, we can then push things forward. If you look at Dirichlet L functions, the averaging formulas are terrific. If you look at elliptic curve families, the averaging formulas are terrible. All right, why do we care about this? So I'll give you one application, and for a while, the worst result I had ever proven in my career. So you can use this to try to bound the order of vanishing at the central point. So why do we care about this? Well, imagine we take our function phi to be non-negative. So phi is non-negative. I have this sum of my test function phi at the zeros. If I drop all the zeros except what's going on at the central point, well, I've made my sum smaller. So if I only keep what's going on at the central point, I get the average rank times phi of 0 is going to be less than or equal to this integral. So this gives me an upper bound. So with some colleagues, I said, well, what if we tried to look at not just the 1-level density, what if we looked at the 2 and the higher level? And so the first colleague I did this with was with Chris Hughes. I recently extended this with one of my students to get the best results you can. And what we were able to show is that the probability that you vanish to order R or higher is some constant depending on n times r to the minus n. So it's decaying, 1 over r to the n. So what's nice about this is the higher level density n you use, the better decay rate you get. Unfortunately, you have this constant Cn, which is growing. So the first result I was able to get is at most like 248% of the time, you will vanish to order at least, well, okay, it's really not that hard to prove something happens at most 248% of the time. There are faster proofs than this. But if R gets larger, then the result becomes non-trivial. And eventually the 2-level density gives you better results than the 1-level density. And eventually the 4-level will give you better than the 2-level. But for small extra vanishing, you actually can get worse results. But this is one of the applications of stuff like this, is trying to bound what's going on. You can also try to play the game in the other direction. And if anybody's interested, I've got some notes at the very end. Can you get some lower bounds for how many zeros you must have, if not at the central point, at least in a small neighborhood of the central point? If I give you a family of elliptic curves of rank 4, we expect there to be 4 zeros at the central point. How big of a window do we need to take around the origin before we're guaranteed on average of seeing 4 zeros? And you can prove results like that. Okay, this sounds like an AA meeting.
We don't know if there's an upper bound for the ranks of the
Did you say, we do not know that there's an upper bound for the ranks?
We don't know if there is or not, right?
Correct. There are, when I was a graduate student, people I think still believed in unbounded rank. But now people believe that there is a bound. I think, has the wind shifted to more people now believe that there is an upper bound on ranks of elliptic curves over Q?
Punin believes there is.
Yes. And Punin school, yes.
Rubin is skeptical.
Right.
So, yeah, I don't know what Elkins believes. He has.
Well, he has the record at 28.
Yeah, so maybe he believes that's the best, and
Right.
The record for all time.
Right. And so what's wonderful is, Punin's and his team's conjectures on what the rank is just a little bit above the highest observed.
The highest is at 20.
Is 28.
Yeah, I think there are infinitely many of up to what 12,
12 or 13.
13, and then it's just a few sporadic past that. It's what
Right.
Punin's stuff goes.
And then like just to motivate people to do it, fine. It just gives like a lower bound.
So I can give lower bounds over families of elliptic curves. And but this is lower bounds on how many zeros you have in a window about the central point.
So you'd be saying that there's really very few.
No. So let's say I give you let's say. So right. So if you assume Butch-Winton Dyer, if I give you a family of geometric rank 4, where I have 4 points that are linearly independent over Q of T, I would expect each specialized curve to have 4 zeros at the central point.
Yeah.
I can't prove that. If I could use the delta spike, I could prove it. What I can do is I can say, if you give me the ability to look at a small window centered at 0,
Yeah.
I can prove that there are 4 zeros in a window.
Okay.
And my window is not nearly as small as I wish.
Oh, I see. So you're not actually
I'm
getting the analytic rank.
no.
You're
No, to get the analytic rank, it has to be exactly at 0. A little bit off 0 is completely different. So I'm able to just show that if you go a reasonable distance, you'll see at least the number of zeros you expected to see at the central point. It could be, right. So you have, if Butch-Winton Dyer is true, you are supposed to have 4 zeros at the central point. I could have 4 zeros not at the central point, but 2 just a little bit above and 2 just a little bit below. And because of the size of the error terms, that would not be inconsistent with the results. And so my question, which I gave to one of my students, was, well, just how far are we allowed to move before, if we don't see any zeros, we know something must be wrong. And so we were able to get a result. And I'm going to work on an extension of this with another student, trying to use the n-level densities to get an even better result. And so if this talk is not absolutely horrible, I would love to come back and say 2 years. And we should have it by then. One of the nice things about being a young student is choosing where you want to go to be a postdoc. You go to certain places so that you can use people's tech files or whatnot. I went to Brown, so I was able to access Joe Silverman's elliptic curve stuff. I'm sure if I had come here, you would have let me use your elliptic curve stuff.
Beautiful pictures.
Okay. Now, okay. So Joe was kind enough to let me use his. So if you haven't seen elliptic curves before, so let's take something of the form y squared is x cubed plus ax plus b. A and b are either integers or rationals, and I'll look for rational solutions. X and y are both rational. So it turns out you could put a group law on this. So if p and q are 2 points with rational coordinates, if you draw the line connecting them and look at where that hits the curve y squared equals x cubed plus ax plus b and reflect, that turns out to be a group law. If you haven't seen it before, you have to reflect to make everything work out nicely. It's a simple calculation of y equals mx plus b, which is different than that b, of course. If you put that in here, if two of the roots are rational, the third has to be rational. And then if x is rational, that forces y to be rational. So r will have rational coordinates. So the reflected point will have rational coordinates. So we can write the group of rational solutions, EQ, as some torsion part plus some number of copies of z. And the number of copies of z is the geometric rank. This is what we were discussing a moment ago. Is it bounded? Can it get arbitrarily large? What can you say about this? The Birch-Swinnerton-Dye conjecture says that that is equal to the vanishing of the associated L function at the central point. And so what's the associated L function? Well, I don't want to go into all the details, but basically I want to count at a prime p minus the number of pairs xy in z mod pz that satisfy this equation mod p. And so I get local data by counting the number of solutions mod p, and I put that together and I build an L function, and it turns out it also has an Euler product, and there's just a tremendous amount you can say about this associated function. And the big one is the Birch-Swinnerton-Dye conjecture that the order of vanishing of the L function at 1/2 is equal to the rank of the Mordell-Weil group. All right, so instead of looking at just one L function, I could look at, let's say, A and B are polynomials with integer coefficients. And Silverman proved that if you choose different integers for t and specialize the elliptic curve, once t is sufficiently large, if your family has geometric rank r, then each curve has geometric rank at least r from some point onward. And then for a while, the question was, well, how is the rank distributed? And for a lot of families, not every family, but for a lot of families, life is as good as you would expect. That half the time the specialized curve will have even sign, half the time they will have odd sign. And so that means maybe in the limit, half the time they should have rank r, and half the time they should have rank r plus 1. That doesn't mean that you only have finitely many of rank r plus 2, r plus 3, r plus 4. You could still have infinitely many, but a lower percent. So if I'm looking at, say, t goes between n and 2n, if only square root of n have rank r plus 5, percentage-wise, square root of n over n goes to 0, but that's still infinitely many. So it's not saying anything about whether or not it's finite or infinite. It's just saying, percentage-wise, the natural conjecture was that half the time you have rank r, half the time you have rank r plus 1. Another way of phrasing this is your rank is as small as possible, consistent with the specialization theorem, which says we know everything has to have rank at least r, and maybe the signs are distributed uniformly. Yes. Yeah, the integers t that I'm using. Yes. What do you do?
To get around half, basically, you have to define.
So what I'm doing is I'm saying, let's let little t range from big N to twice big N, that. And so I have n values of t, and I see what fraction of the time do I have rank r, what fraction r plus 1, r plus 2, r plus 3, and so on. And it's conjectured in the limit for a nice family of elliptic curves. Half the time it should be r, half the time it should be r plus 1. There are some families of elliptic curves where the sign is not 50-50. Sometimes it's 100-0. Sometimes it's some number between 50 and 100. So depending on what kind of reduction your curve has, you can create certain interesting examples. But for generic family, and as long as you put generic, whenever you give me a counterexample, I will just say, well, that's not generic. And it just, it's a really good cover your, this is being recorded, so I'll stop there. This is just, for most nice families, we would expect half the time rank r, half the time rank r plus 1.
On Silverman's theorem, isn't it, we actually do t rational too. And isn't it just like finally the exceptions?
Yeah, I believe so. And I think
Then
it's,
you can order by height.
right, you can order by height. And I think his theorem is also effective. I'm not positive. I can't remember.
He does ineffective stuff.
He does ineffective stuff as well. And there's a great joke I can share after the talk on the value of ineffective theorems that I do not want to record. So what I want to do is I want to talk about some data. And so back when I was younger, I actually used to code a lot in Paris. I used to do a lot of numerics and try to use that to get a sense of what was going on. And so what was observed is that in a lot of one parameter families, we observed about half the time the rank was R plus 2, R plus 4, R plus 6, and half the time the rank was R plus an odd number. That's good. And we observed about 48% of the time the rank was R plus 1, and only about 2% of the time was it rank R plus 3. Okay, pretty good. But on the even side, the R and R plus 2, in a lot of families, around 18% of the time, you were seeing rank R plus 2. And so people thought maybe there's some kind of excess rank. If anybody's ever done any calculations with primes, you might be a little bit surprised to learn that 40% of all integers are prime and 20% of all integers start a twin prime pair. And I'll prove this to you quickly. So if you count all the primes up to 10, you get 2, 3, 5, 7, 4 primes. And then 3 and 5 both start twin prime pairs. So 40% of integers are prime, 20% start a twin prime pair. If you are skeptical, I will double the range of computation, go up to 20, which gives 11, 13, 17, 19. So again, 40% of all integers are prime. And again, 11 and 17 start twin prime pairs. So,
in other words, start at 101.
but what time are we stopping now? That's 3 digits. That's
101, 103,
Oh,
107, 109.
oh, there we go. Yes, yes, thank you. Oh, excellent. Yes, and that was a randomly chosen non-planted question. Yes, excellent. So you would never make a conjecture on prime. Oh, sorry. You should never make a conjecture on primes. Only going up to 20 or 100, at least 110.
Yeah.
Well, if you look at what's going on for elliptic curves, it's really the log of the conductor of the elliptic curve. This is something that comes in the functional equation that controls what's going on. And the log of the conductor in the realms that we're looking at is really only on the order of 20. So even though we're seeing this 18% of the curves in the family having rank R plus 2, we're not really going far enough. Even though we have millions of curves in some of these families, we're not really going far enough to see truly generic behavior. Eventually, Mark Watkins and others went far enough to see that 18% decrease in some families. So what I was trying to do is I was trying to understand, why do we have some of this excess rank? Why are we seeing rank R plus 2 as high as 18% of the time? And so one of the things I was looking at was the first normalized 0 above the central point. I was trying to see, what is the impact of having more zeros at the central point? What does it do to the nearby zeros? Does it push them up? Does it attract them? Does it repel them? Does it push the closest one more than the second closest? Does the effect get smaller the higher you go up? And so I was just trying to gather some data to then lead to the theory. And so I don't want to go into too much technical detail. So there's a couple of natural theories that one can do. One is, we believe random matrices should model what's going on. So I could look at SO even matrices. One possibility is the independent model, where let's say I want to have 2R zeros at the central point. Well, let me just look at SO even matrices that have a 2R by 2R identity block up here, 0, 0, and then G, which is of a smaller size down below. Then these 2R eigenvalues of 1 will be completely independent from those eigenvalues down there. So this is the independent model. The other thing I could do is I could go back, could roll up my sleeves, I could do the probability calculations, I could write down the densities, and I could say, well, I want to put in some eigenvalues of 1 and allow them to interact and see how that changes the density. And that gives very different answers. And so if you calculate what the Fourier transforms of the different one-level densities would be, you get a different answer for the independent versus the interaction model. And in my thesis, I looked at families of one parameter families of elliptic curves over Q of t, and I was able to show in the limit that it's the independent model that's right. So in the limit, the interaction model is wrong, the independent model is correct. And if the family has geometric rank R, you would expect each curve to have at least R zeros at the central point. There is a term over here, R times phi of 0, which is exactly what you would expect from Birch-Swinnerton and Dyer. I don't know that this is a proof. Yeah, this is, of course, not a proof of Birch-Swinnerton and Dyer, but it's at least behaving consistent with that. And other people had seen similar stuff like this before. And so the question was, can we come up with a model that will describe what we're seeing? So for finite conductors, I want to describe this excess rank. And then as the conductors go to infinity, as I go down the line, I want something that's going to converge to this independent model. And so to give you a sense of what things look like, this is the distribution of the first normalized eigenvalue above 1 for SO even matrices. So the probability density starts very high, drops off. Look at the first normalized eigenvalue above 1 for SO odd matrices, you can see that there's a bit of a repulsion. And then I start looking at different families of elliptic curves. Based on the time, I don't want to go into too much detail. So I'm looking at 209 rank 0 curves from 14 rank 0 families. There's no eigenvalue, there's no 0 at the origin, but it looks like there's a repulsion. This looks closer to the SO odd, where I know there's an eigenvalue at 1, than the SO even, when there's no eigenvalue at 1. So it looks like I'm seeing repulsion even though there's no 0 there. I then increase the conductors. And when I increase the conductors, it looks like the repulsion has decreased. You can see over here, the average mean was like 1.36. When I increase the conductor, here it was 9.9, it was the largest, now it's 15 to 16. The mean has gone down to 0.86. So the repulsion seems to be decreasing as the conductor is increasing. You can look at this for a large number. This is one of the most bullshit slides I think I've ever done in my life. I'm looking at 35 curves. That's not that many. The reason is I wanted to have 35 curves with small conductor up to 16.1, and then 34 curves with larger conductor. You're getting up to 23.3. This was taxing the computers I had as a postdoc, to do these calculations. But you can see the repulsion decrease as you are increasing like this. And then I started playing lots and lots of guessing games. I started looking at everything I could. I looked at rank 0 curves from rank 0 families, rank 2 curves from rank 0 families, rank 2 curves from rank 2 families. Every statistic I looked at, just to summarize all the different slides, it seemed like what was happening is you have your gaps between your zeros and they're glued. And then if there's repulsion, it's like you take everything and you just shift everything up together. That the repulsion seems to be shared equally. And so this was an interesting clue. And then with John Keating and Nina Snaith from Bristol and Eduardo Duenas, and then graduate student of Nina and John's, Du Kim Huynh, we then came up with a theory to try to explain what was going on. And the points we had to address was the repulsion increases with increasing rank. The more zeros we have at the central point, the more of a push you get. As the conductors increase, the repulsion seems to decrease. And so briefly, I've got, I think, about 5 minutes left. Okay, so briefly, here's the Odlyzko plot again. Whenever you see beautiful agreement between theory and experiment like this, you celebrate, and then you get to work and you subtract off the main terms and you look at what's left over. And after you subtract off the main term and you look at the fluctuations, that's not random noise. There seems to be some lower order behavior going on. And so the question is there similar lower order behavior that we can essentially use to model what's going on for finite conductors? And it turns out there is. What's going on is we haven't hit the limit yet. So there's a couple of things we need to do. The first is a very small tweak, is we have to adjust the size of the matrix we're comparing it to. It's a little bit technical to just match things up. It makes some difference, but not a tremendous difference. But the big one is that in general, it's very hard to show something is exactly 0. So this was the comment from before. How do you know they're actually at the central point as opposed to not really close? Well, for elliptic curves, you can prove that the value at the central point is equal to some constant which is computable that depends on the elliptic curve times a rational number with a bounded denominator. So let's say we know I've adjusted things so that that constant is 1, and let's say I know the denominator is at most 100. If I calculate what's going on at the central point, and I can show the value at the central point is at most 1 over 201, well, it's got to be some kind of integer over at most 100. So for at most 1 over 201, what's the only integer it could be? It's got to be 0. So if you can then calculate it close, it then reduces to being an exact value because I know it's a rational number. And so I just have to show that the only one it could be would be 0. So the discretization of the values of the elliptic curve L function caused a lot of trouble. And so the model that we came up with was, don't compare this to all matrices. Don't compare it to all SO even matrices. Compare it to SO even matrices whose characteristic polynomial, the characteristic polynomial of the random matrix, is the analog of the L function of the elliptic curve. compared to the value of the characteristic polynomial is at least a certain constant. And so we're basically called the exercise ensemble. We're throwing away anything that has a very small value of the characteristic polynomial at 1. We're saying that will collapse down to being 0. And when you do that, we now get an incredibly beautiful result. I'll just switch to the last slide. And what you see now is we get this, jagged line, which is beautifully fitting the curve. And so by putting this into play, that we're now going to adjust the size of the matrix we compare with, and we're going to throw away any matrix whose characteristic polynomial is, too small. That's going to be the analog of what's going on for the elliptic curve. And so I'm finishing up right now with some students that's unfortunately not quite ready to show yet. What if you look at other families of cuspidal new forms where you have other kinds of discretization issues? How does that impact what's going on with the zeros as well? So thank you.
Questions?